Hi everyone, welcome to the Z content on analytic functions. The origin of this analytic function would have been from the number theory or from the theory of differential equations or algebraic functional equations, and especially in the mathematical physics, the entire realm of functions, especially this analytic function, holds the undisputed place in finding the solution of the differential equations. So what is the need of studying the functions and the complex variables? Actually, there is no any quadratic equation which has got a solution in the real numbers. So apart from the real numbers, there is an surprising solution was hidden. So those surprising solution was formulated by the mathematician called Cardano before 400 years. So he started to work with the imaginary roots. Then came the mathematician called Euler, who gave the value for the imaginary parameter called I. There is imaginary number called I, which possesses the value of root of -1. And the rigorous theories was formulated by the Hamilton, Gauss, and many others related with this imaginary complex number. And what is the significance of this analytic functions? These analytic functions can be represented in forms of Taylor series or in the form of Lorentz series. And most specifically, it can be used for any transformation equations like Fourier, Laplace, etc. The main thing is all these equations can be used to calculate the solutions of many differential equations. So such analytic functions finds its application based on the solutions for the heat conductions and the problems based on fluid flows and the problems based on electrostatic analytic functions. So this analytic function have got a variety of properties, make them ideal for many applications. So the basics of analytic functions starts with the Cauchy-Riemann condition. Before getting into this Cauchy-Riemann condition, let us know what do you mean by an analytic function. So the analytic function is defined by the function called f of z if it is differentiable at z is equal to z naught. What is z? The point in the space. What is z naught? Again, it's going to be the random point in the space. So f of z is said to be analytic at the point called z is equal to z naught if it is differentiable. If it is not differentiable, then it is not an analytic function. So how to check whether the function is differentiable or not? So many conditions are there. One such condition is Cauchy-Riemann condition for differentiability. So the need is now you need to check whether the function f of z is differentiable or not. If it is differentiable, then the function is analytic function. So how to check whether the function f of z is differentiable? We have to apply the Cauchy-Riemann conditions. So there is a page of theory based on the Cauchy-Riemann conditions. To put it in a nutshell, the f prime of z. What is f prime of z? It's going to be the derivative of f of z. So f prime of z is represented by df by dz. And what is f? F is nothing but a function. What is z? Z is going to be the complex number, which is represented by the real number plus imaginary number. It is u plus iv. So df by dz, how can I write this df by dz? This is nothing but limit f of z plus delta z minus f of z divided by delta z. So there is going to be the change in the complex number and we are going to find the function with respect to the change in the complex number and subtract it from the real function so that you may end up with the derivative. So to put it in a nutshell, limit delta z tends to 0, which is nothing but delta f of z by delta z. And there is some rigorous explanations and derivations over there where we end up with the Cauchy-Riemann conditions. To simple way to remember, dou u by dou x should be equal to dou v by dou y, and dou u by dou y should be equal to minus of dou v by dou x. So if that condition is satisfied, then the function f of z is analytic function. Now there is a twist. If the Cauchy-Riemann conditions are satisfied, then f of z is differentiable. So what we formulated in Cauchy-Riemann condition for differentiability is, if f of z is differentiable, then the function f of z obeys and Cauchy-Riemann conditions where it shows that f of z is an analytic function. Now we are going to put the sentence in a reverse way. If the Cauchy-Riemann conditions are satisfied, then this f of z is differentiable. So there is a simple explanation to understand this. So what is df by dz? What we have done in the last slide. That is limit delta z tends to 0, delta f of z by delta z. And what is this delta? Delta is going to be the change. What is this z? U plus iv. So what is delta f of z? Nothing but dou u by dou x plus I times dou v by dou x into delta x. The same thing have to be done with respect to y, where the change should be done with respect to the delta y, right? And here in the denominator, delta z is represented by delta x plus I delta y. So I hope you can find the two similar terms in the first and the second term. So the term within the bracket is quite same. So we can take that as a common term, and you'll end up with the term delta x plus I delta y, which can be taken as a common in the numerator, which gets cancelled, and you'll end up with the simple form, that is dou u by dou x plus I times dou v by dou x. Or I can also represent it in the form of 1 by I times dou u by dou y plus I times dou v by dou y. So both the conditions are right. So one thing we need to have it in mind. If the function f of z is analytic, then the function f of z is differentiable. If the function f of z is differentiable, then it should satisfy the Cauchy-Riemann conditions. Now the statement is in the reverse way. If the function satisfies the Cauchy-Riemann conditions, then the f of z, function f of z is differentiable. So there are many other properties which are related with the Cauchy-Riemann conditions. So next is going to be related with the integration. How far the Cauchy-Riemann condition obeys in case of integration. So it's a beautiful theorem. That is, if the function f of z is analytic in a given region R. For example, a region is given for you with an coordinates in x-axis as well as in the y-axis. So if for any given region, if the function f of z is analytic, then if you draw any closed path in that region, then the contour integral of that function f of z around the closed path C is equal to 0. Simple way. If the function is analytic, then the integral f of z dz is equal to 0. How to prove that? This can be done by using the Stokes theorem. That is, the surface integral is equal to the cross product of the volume vector is equal to the closed integral of the same vector. So what is this v dot delta? What is v? V is nothing but which has got two coordinates. Since here we are imagining two coordinates, so vx, vy. So Vx dx plus Vy dy. And similarly, on the right side, we do have got a cross product between del cross V. So how to do the cross product? You know, what is dou? Dou is nothing but dou by dou x, dou by dou y. And similarly, I do have got ij. And what is V? Vx, Vy. So if you take the cross product of del cross V, you will be left out with dou Vy by dou x minus dou Vx by dou y. And since here the differential parameter is d sigma, both the derivatives should be taken into account, and also the integration is the surface integral. So we should be more cautious in introducing dx and dy on the right hand side. Now, by making use of this formula, the formula which we have seen in the first line, there is the integral f of z dz can be done by using the formula u plus iv dx plus I dv. What is u plus iv? F of z is represented by u plus iv. And what is dz? Dz is nothing but dx plus I dy. So do the product and separate the real parts and imaginary parts separately, and you'll be end up with this equation. So just substitute this equation here, and you will find that the integrals cancel among each other, and it will be end up with 0. So this is what the theorem is. If the function f of z is analytic in a given region, then the closed integral f of z dz is equal to 0. So we have seen two theorems based on this. One is Cauchy-Riemann condition for differentiability. Next is Cauchy's integral theorem. Another important theorem based on this is Cauchy's integral formula. What is this Cauchy's integral formula? For example, if any point z0 is given to you, and if you are asked to find out the function f of z at that point called z0, then you can make use of this Cauchy's integral formula. What is the condition for that? The function f of z is analytic within as well as on the closed contour C, Then for any point that is it not, whichever it is going to be referred, or the point where you are going to check whether the function is analytic or not, or the point where you are going to apply this Cauchy-Riemann condition and you are asked to find out the function f of z at that particular value is nothing but is it not. So how can we make use of this? Simple formula. F of z naught is equal to 1 by 2 pi I integral over C f of z by z minus z naught into dz. What is z naught? That's going to be the random point or a new point where you're going to determine the function f of z. What is z? Z is nothing but the point which is already defined, or it can be assumed as an origin. So here the proof goes like this. So hope you could see a kind of an imaginary region which has got a closed contour called C, and the inner contour is represented by C naught, which is connected by the two lines called L1 and L2. So how to find the formula here? So here we need to take the integration in all the four terms. First I need to take over the integral C, that is over the closed contour C, and then I have to take over the line integral L, and then again to the closed contour C naught, and again the line integral L2. So all this additions of all the functions, when I take the integration of all these four terms, should be equal to 0. So based on this, you rearrange the terms accordingly and you apply the formula based on the f of z over the closed contour, which is given by r into e per I theta. So substitute those equations and you will be end up with the simple formula that 2 pi I into f of z. So the Cauchy's integral formula is this. If you want to find the function at any given point called z naught, just you can make use of this formula in a straight away. F of z naught is equal to 1 by 2 pi I integral over C f of z divided by z minus z naught into dz. So till now we have seen three theorems. Number one, we should know what do you mean by the function f of z is analytic function or not. Second point, and what is the condition for the differentiability? There is Cauchy-Riemann condition for differentiability. Next is Cauchy's integral theorem. Next is Cauchy's integral formula. And the fifth theorem is about Morira's theorem. This is something related with the Cauchy-Riemann conditions. That is, the theorem goes like this. If f of z is continuous, and if this integral is equal to 0 for every closed contour, then f of z is analytic in this region. So this is going to be some sort of reverse statement of the Cauchy's integral theorem. There is, in case of Cauchy's integral theorem, we would have been stated like this. If the function f of z is analytic in the given closed contour C, then integral f of z dz is equal to 0. Now we are going to put the statement in the reverse way. If the integral f of z dz is equal to 0 in any closed contour, then f of z is analytic in the region. So there are many other theorems which supports this analytic function. So let us meet in the next module with some interesting functions. Thank you.